Okay, so it's 1 o'clock here in the UK time, so let's make a start. So today, this is a third of the speech in our UNESCO Chair and SIMA Webinar Series. So it's really our great honor to have a Professor Philippe, Gourbesville in here to give us a talk. So I suppose, I think everybody know Philippe, really well because he is first of all is a famous academic in the field of hydroinformatics and water management, and secondly he's a current president of our IAHR, so the International Association for Environment Engineering Research. So I think this is the biggest professional body in the hydro environment field. So I think I suppose I think most of people attending today would know Philippe already. So if not, and then in here I just give Philippe a very brief introduction. So Philippe is the professor of hydroinformatics in University Côte d'Azur. I think I hope I pronounce it reasonably. I think and also vice president of the Asian Water Council. Meanwhile, he also holds the prestigious distinguished professorial appointment at the Institute of Water Resources and Hydropower Research. He brings remarkable expertise in water management and hydroinformatics. Again, a role with no academics in this field. So apart from the professional expertise, he also brings in leadership, in coordinating many European research projects and also, education program, including the famous EURAQUA MSc program in hydroinformatics and water management, which I was lucky enough, to be involved as well when I was working for Newcastle. So apart from this, I think, Philippe's almost everywhere. He's really active, internationally. So his experience is spanning Europe, Asia, Africa. So I think I shouldn't really talk about more. I think I should really give, keep this short. And again, everybody knows Philippe already. So before I give the floor to you, Philippe, and then I just briefly mention about our next talk. So I think our next webinar would be our fourth one for the 12th of March, would be delivered by Professor Heidi Nept and also his student and Anit Lee, from MIT. So I think this would be another great, talk. So I hope, many of you will sign up, for this one as well. Apart from that, don't forget we will have our SIMA conference 2025 after our successful one in Loughborough last year, and then we will have our second one in Chengdu in mid-September this year. So here gives the information. So for those, I think never been to Chengdu before, I can promise this exciting city, vibrant city, and then it's a hometown of Panda. So I think you can't miss it. And so hopefully I can see many of you there. So, okay, I'll stop sharing, Philippe, and then I'll give the floor to you so that you can share your screen now. Thank you.
Okay.
Oh, before, while Philippe is sharing his screen, and then please, I think during the talk, if you have any question, type them, at the check box, and then after that, and after Philippe's speech finished, and then I'll pick it up, and then so that I think we can get a Q&A section, together with Philippe. Thank you.
Okay, thank you very much for the very kind introduction. Can you confirm that you can see my screen? Is it okay for everyone now?
Yeah, yep, see really well and hear well, yeah.
Okay, thank you very much. It's a real pleasure for me to be there today, and thank you for the invitation. It's an interesting exercise, and I'm very happy to be with you and to try to share a little bit about my experience regarding flash floods, trying to address a little bit regarding challenges, needs for mitigation and adaptation. First, to apologize regarding maybe the quality of the video and maybe the quality of the sound. Currently, I'm in Cambodia. I'm on the Mekong River, and the condition of access to internet are a little bit chaotic. So I hope the things will go smoothly, and I will try to do my best. So. Nevertheless, I would like to try to start the presentation by trying trying to explain a little bit about what I will try to say regarding the flash floods. I'm sure this is something which is very commonly known by most of the participants today. You have on the screen some of the pictures of the recent events that you may have still in mind, maybe not totally in mind, because in fact we had so many recent major events, so located in Europe, but also in Africa or in Asia, that all of those events have deeply marked the of course local communities, but also at the international level. So this is some of the interesting pictures that commonly you see when we are talking about flash floods and what we are seeing. I would like just to show you a few graphs that are coming from reinsurance companies. So, you know, reinsurance companies are making a very essential job. They are covering the risk of the insurance companies. So, in fact, they are there for supporting financially the risk of the standard insurance companies. And what has been mentioned by Munich Re, which is one of the two biggest and largest reinsurance company, is that the number of losses relevant to extreme event is increasing. So it means we have more flood events and with more severe damages. You have this picture which is showing the situation in Valencia in Spain. I'm pretty sure everyone has in mind the recent consequences of our colleagues and friends in Spain. And as you see on the screen, the blue and the green curve are increasing. Regarding hydrological events and meteorological events. Over the last 20 years, we have seen a very serious increase of the events and also increase within the damages. If we look at the details over the years, so this one is also a document which is coming from ICRE. You see the distribution of the different type of events, and you see that hydrological and meteorological events, blue and green, have increased strongly over the past years. So especially since 2000, we have seen the number of events. Of course, you can do the link with the climate change, the situation regarding new meteorological, hydrological processes, but also with the increase of the vulnerability of our modern environments. We are facing more damages because the vulnerability has not always been totally assessed and totally prevented of major risk. If now we look at the number of flood events, is I think quite important to have in mind. Annually, we have something which is around 350 to 400 events. If we look back 40 years ago, it was less than 70. So it's just to give you an idea on how many years we have moved from something which was still, I would say, reasonable, or I would say easy to handle, to something which is now affecting most of the world with dramatic consequences, and we will see some example in a moment. So this is something which is important. And recently we have seen a new report which is coming from Swiss Re, which is showing the annual loss from severe convective storm events from 1994 to 2023. So you see this increase, which is extremely severe, and you see this trend, so which is quite impressive. And you see that the magnitude has strongly increased with a very major cost. Right now, this is the largest cost for the insurance and reinsurance company. It became the first risk to be covered during the past 2 years. So this is something which is very important. I did the exercise to try to look through the very well-known EMDAT, which is storing this database, all the major events regarding flooding, and you see the evolution. So we have right now every year something which is above 25 major events, as we had less than 10, I would say less than 10, 15 years. So this is something which is important. In average, we have less victims, but we have bigger damages. So this is something which is coming from insurance and reinsurance company, but also for. So it means it's a very important challenge for our modern society, which is safety, how we serve economical activities. This is also something which is extremely important. In most of the cases, the media are reporting immediate effect of flooding. We see images about the flow from the rivers and so on, but very few reports are coming to the public regarding the reconstructions. And this reconstruction phase for one very short event is not for a few weeks, but most of time for several months or even several years before to have the reality and the standard life coming back to those communities that has been affected. This is something which is extremely important. There is a lot of work to push on and to try to move on to try to address this process. One of the example, and I took this one because it's already a little bit old. It's 2023. I do not know if everyone remember that, but it took place in Libya. Of course, this is not a country which is well known for being affected by such a type of event, but for one exceptional situation, having rainfall and also the collapse of several infrastructures, hydraulic infrastructures, we came with a major disaster with several thousands of victims. So this is something which is extremely severe. You see the magnitude of the destruction, and I will come in a moment to these type of things to try to explain a little bit about how these processes can challenge, of course, hydrological processes, but also question how we design the cities, how our city can be ready to be flooded and can face such a type of situation. We have to preserve the population, and then we have to try to preserve the organization, the services that are within the city. How can we do that? And I think this is a challenge not only for the water people, but this is a challenge for the urban planners, for the architects, and for the people who are planning at the city and the regional scale. Let me try now to come to something which is a little bit more operational and trying to address the problem of flash floods, especially generated by extreme runoff due to meteorological situation. And the example I would like to take is around the Mediterranean Sea, just because we had the chance to have many examples, and so we can share a little bit of this situation. For my definition, and from most of the practitioners, the situation start to be difficult to manage and to handle in most of the urban environment when you get an intensity which is higher than 70 millimeters per hour. If you look at different engineering code, including for the railway operation, for example, in India or in other countries in Latin America, you will find this threshold. If you are equal or above 70 millimeters per hour, you are sure you will have problem. Whatever you have designed, even following the code and whatever the regulation are, you can be sure that something will happen and it will affect the normal condition of services within the city. In most of the cases, those extreme rainfall are coming from convective storm, and they are frequently combined with stationary situations. So we have the convection, creation of the storm itself, and this storm will stay blocked for a duration, can be half an hour, 1 hour, or sometime longer. And of course, it's generating massive runoff. I will come to that. We are reaching runoff values that are not observed in natural environments, which are most of the time observed in urban environments. But in fact, due to the high intensity, we have something which is 70, 80 millimeters, 80% of the water which is produced will go as runoff. In the case of the Mediterranean Sea, the situation is mainly driven by the fact that we have warm and humid air, which is coming from the south, coming from the African continent, crossing the Mediterranean Sea and going through the sea and reaching the south part of Europe. Could be Spain, could be Italy, could be France, or it could be Greece. In addition, we have orographic effect. You know, in most of the cases, for the Mediterranean coast, for the north part, we have mountainous environment. So it means frequently the wet air is stuck and blocked by the mountains and cannot go over, so which is generating massive rainfall events. You have an example on that slide. What you have on the picture is not AI generated. This is a real picture. So you can see the small extent of the event itself, and you can easily imagine how strong can be the rain below this structure. Something I would like to mention is also the size of this convective cell. Sometimes we have units that are very few square kilometers, 2 to 5 square kilometers are extremely frequent. So it means we should be ready to have this intensive cell coming only over a small phase and to see how we assess the potential effect. This graph is showing how it's going on the coast in France. Most of the time, we have the wind from the south being loaded with strong humidity of the sea and then reaching the coast, being blocked by the mountain, could be from the Pyrenean side or it could be by the Alps side on the east side. And of course, we get strong runoff taking place on those steepy slopes. Or, of course, we have high velocity, high runoff, high possibility to mobilize sediments from fine to coarse and even bigger than coarse, and with very severe consequences, as you will see. Something which is quite important is to see that those type of effects are most of the time coming at the end of summer, beginning of autumn. So you have on the screen what we call now mitigation. We are more familiar with hurricane and typhoon more in the west to the Caribbean or more in Asia for the typhoon, of course. But we have also mitigation over the Mediterranean Sea, and you have this example of October 86 and the other one in September. In most of the case, we have this type of condition generating flux from the south, moving to the north and traveling along the coast and generating massive rainfall. Why do we have such a type of processes? The main driver, this is quite simple, this is a sea temperature. And in fact, now we know that when we have in September, early October, a sea temperature which is above 24 degrees, the sea temperature is equal or higher than 24 degrees, we may face this type of situation and generating this type of conditions that may affect the coastal region. So it could be Spain. You see again the France, Italy, and the different small islands that are in the place. Here you look at the on the screen. You have how many storms we have observed over the past decade. I'm not saying that in the past we had less, but at least we had less observation, and we see that over since 20-25 years, the number of events has increased. Moving from below 10 to something which is higher than 20. So it means the conditions are becoming extremely more serious. I would like now to try to share with you one example, one case that took place in Nice and along the Riviera. It was another 15. So as you said, at this early situation of October 2015. The rainfall for the most affected places was more than 260 millimeters, so which is quite high, in 2 hours and a half. Number of victims, 21 people died during this event, and we have direct damages more than 1 billion euros, so which is quite significant. Of course, the magnitude of indirect damages is higher than that. So it means it's roughly between 2 and 3 billion euro of indirect damages, economical losses, perturbation on the services in economical activities. It started on one evening. You see a soccer match was planned at the stadium in Nice, and it started to pour quite seriously. The people had to didn't evade the stadium. It was maybe not a very good idea because it was pushing a lot of people outside of the stadium, taking their car and making traffic jam and being potentially exposed to a risk of flooding. Hopefully nothing was happening at that time, but it was a meeting of them, and I will tell you what have been the consequences. how was the event? The event was coming from the west and moving to the east and was affecting the coastline. So you see it traveling from Frejus and going in direction to Italy. On the right side, you have an idea regarding the electric intensity, electric activity, number of flash that took place during those different events, and the rainfall was mainly affecting the city of Cannes, so with close to 200 millimeters and a little bit less around. Nice received only 100 millimeters, so I would say half, over 20 kilometers. You see the big diversity of quantity of rainfall that you may receive. So the rainfall was almost stationary for 2.5 hours and was generating massive runoff. Nice is one of the greenest French cities. You see a lot of gardens, so it's called very frequently the garden city. So you can see that on the picture. Nevertheless, this is how it was in the street. So we had very, very high velocity flows. So you see more than easily 1 even to 2 or 3 meters per second for the most steepy street, deeply affecting the traffic and having the behavior of the people being also a little bit not very realistic. We have people affected and being washed away by this type of things, and this is something which is an example of not to do or not to how to behave during such a type of situation. Obviously, one of the parts that was the most affected during was sound structures and especially parking lots. So this is the movie festival theater in Cannes. You see the water coming from the storm drainage system, blowing totally and destroying part of the roads and having the basement of the different buildings severely flooded. In fact, most of the victims were people trying to rescue their car, their bike, or their motorbike from the groundwater. Over the 21, I would say 18 or 19 of them were people who didn't realize how serious it was to go in a basement that is flooded, and with the capacity they have impossibility to remove out of this basement, and they were just trapped within those structures and with no capacity to escape, and they were just dying, unfortunately, during this event. So you see some of the consequences on the city regarding the different facilities. On the left side, this is the access to the station, the railway station. So you see the access is just full of water. So it means the train and the passengers were blocked during 2 nights with no possibility to evacuate from the train. And of course, this is not something that you may plan in advance. Another important effect is the quantity of sediments that came during this event. The region is very steepy. The runoff was extremely heavy. The quantity of sediment transported was massively affecting the network, and which was totally saturated and making the things extremely difficult. Of course, the car are a good tracer regarding the flow velocity. The car can be removed very, very easily. We had more than 2,000 cars totally destroyed during the event, and of course, it's explaining part of the cost. Something I would like to mention is the event, in fact, was not really original. We had a similar event that took place in the past. You see, it was at the beginning of the 20th century. It was affecting a small village in a little bit in the upstream part of the region of Nice, and we had a rainfall which was potentially more than 150 millimeters, having severe consequences on the place. At the same time, if you look at the rainfall events, we had in Nice in the past already events that were reaching important values. So you see 180 millimeters in 24 hours. So it means that during those events, you need to anticipate and to be ready to be seriously flooded. As I said, the design is cannot cope totally with this type of magnitude. Why did we had so many victims, and why, in fact, the people were not so well prepared in 2015? It's quite simple to understand. What you have on the screen is what is produced by Météo France and which is used by public services to broadcast and to provide information to the public. On those days in October in 2015, the level of alert was only orange. So it means it was not the highest level. The highest level is red. And when you get the red level, it means you have to stop some of the public services. And based on the information in 2015, it was not sufficiently highly identified with a high risk to broadcast this red alert to the public and to avoid and to restrict some of the services. So the situation was, in fact, information were not sufficient to take the relevant decision. You see on the screen a reanalysis of the events. You see that we can potentially, with a model, easily simulate properly the quantity of rainfall. So it was made with a 1 kilometer resolution, but this simulation came 24 hours later, just because the capacity of simulation at that time was not sufficient to anticipate and to produce something highly accurate to match the spatial resolution that we had. I would like to take another example. It was in 2015. Unfortunately, 2nd of October 2020, we had another storm coming again over Nice and the region. So it was not targeting the coastal region, but it was a little bit more upstream. And you see on the screen how the storm was coming once again from the south and was blocked by the mountains. We had an extreme rainfall, more than 500 millimeters in 5 hours. So this is one of the top 10 rainfall never recorded in France. And we had 9 victims only, so which is of course already too high, but which is in some extent much better than the situation that we had in 2015. And we had 1.5 billion euro damages over the different villages. Something which is very unusual and something which is very, very exceptional. For this event, we didn't have one convective cell, but we had 3 convective cells together. And this one is extremely unique and very rare. It was the first time that it was observed in Europe. So we had those 3 red cells staying and being stationary for almost 5 hours and pouring water over the, I would say, upstream part of those catchments. So this is something which is very unusual. And this is something that has never been observed. Of course, it may took place in the past, but it was never recorded because we didn't have sufficient images or radar capacity to identify. You see again on those 2 maps how it was affecting. And on the right side, you see the shape of the Var catchment, which is arriving near Tunis. And you see that, in fact, the city and the part that was the most affected is the Vesubie catchment that was concentrating most of the rainfall. So the village and the part of the valley which was the most affected is the Saint-Martin-Vesubie. You have the beautiful landscape during the summer. It looks like a little bit like Switzerland. And of course, a teeny stream with something which is less than 30 cubic meters per second, I would say maximum, what we observed. The situation was totally different. This is how it was. And if you look at the video which has been recorded at that place, in fact, the teeny stream that you saw on the previous pictures was expanded from 5 meters to more than 75 meters in few minutes. In half an hour, we had not only 1 stream, but 3 parallel streams and finally merging. So you see how the things were changing in an extreme quick way and how it was affecting the environment. It was affecting the river, but it was affecting construction all around. You have the example, the embankments, everything has been destroyed. I would like to mention that those constructions were not new. It was historical constructions that have been there since centuries. So it means the process and the phenomena we have seen on that day was really exceptional. And for me, it's a morphological process. This is not hydrology. This is something which is higher. You see the quantity of sediments, what is moving. You will see the small house that will be totally washed away. So this house has more than 100 years and it was safe over years. So it means most of the floods that they had before were never affecting the things as it has been for this place. You see now how the village looked like. So the river that we saw before was on the right side. You see how the valley has been totally reopened. So we moved from something few meters to more than 150, 200 meters. And obviously most of the road infrastructures have been washed away. Here it gives you an idea on the quantity of sediments that have been moved. So this is more than 4 floors of high of the house that has been entrenched in the riverbed, and how it was even moving building totally during this type of event. Here you have an idea regarding the power and the how strong was the transport of the sediment. This is impact of the stones arriving on the blocks, on the structure of the house. The house is naturally filled in with the coarse sediments, making it totally saturated. It's just give you an idea on how the destruction was and how the different houses were affected. So it was something extremely high, extreme magnitude. All the monitoring stations we had on the catchment were destroyed. So it means most of the places we were supposed to record discharges have been totally washed away, just because the stream or the riverbed has been so much enlarged that most of the stations have disappeared, including the bridges. So most of the bridges have disappeared. But at the same time, as I said, we had only 9 victims. Conditions were much more extreme, but we had only 9 victims. Why? For basically 3 reasons. First, we had a more efficient forecast system based on observation and models. You will see in a moment some of the results. We had a better efficient warning procedures. And third, this is obvious and this is extremely important to understand. Following 2015, local population have understood better the risk and was much more ready to react and to understand properly what to do and what not to do. Just to come back, I said better forecast based on the model. So this is what came and what was produced during the previous day, and what has been generated by the model over the 24 hours before. Information coming from the meteorological services was precipitation with a high risk. They were seen over there is more than 300 millimeters. Recording that we had 500, but the people were able to say we will have more than 300. So it was sufficient to say, okay, there is a sufficient high risk to initiate and to issue a red warning. So this is some of the things that have been produced that were used for producing the alert message to the population. So if we look back to how it was mentioned, so the event took place on the 2nd of October. On the 29th, the risk was identified as weak. On the 30th, it was a medium risk. On the 1st of October, it was orange vigilance. So it means it was already red alert one day, orange alert one day before. And we moved to the red alert 6 hours before the event itself. So it was sufficient for the population to react properly and to say, okay, I know what to do and I know potentially where I can be safe and be in a position that I can be preserved of the flooding. So this is the same map of what I presented for 2015. And you see that in this case, we had orange alert and we had a red one, which was located around Nice. Of course, the surface is still large and it could be, I would say, very disturbing for economical activities, because we are including a lot of municipalities that potentially are not directly affected by the event. But the way of doing the things was to promote this type of event. Now, how can we try to anticipate and try to prepare better regarding this type of situation? One of the possibilities to try to simulate the unexpected. So this is now a big discussion for the practitioners who have to rebuild public infrastructures, roads, bridges. What are the hypotheses that we need to take into account? Do we have to redesign how it was before, or do we have to take into account the recent event we have seen in 2020 and to do the things? Of course, there is a tremendous increase of the cost for those infrastructures, which is also challenging the question, do we have to keep people in those valleys? Because in fact, we have a low density situation, and investment in public infrastructures can be equivalent to the private goods that we are protecting. So there is a debate, which is not only technical, but it is also a debate for the society to choose what is a priority, what do we have to do in those places. So few points regarding the lesson learned regarding this storm, which was called Alex. Better preparedness, better reaction of the population due to the previous events. You are always reacting much better when you have been exposed. It's better to be exposed and to know what means flooding if you want to move the things. So now the question is, how can we anticipate exceptional situation? How can we evaluate impact? So risk resilience measures. So physical mitigation will be not sufficient because we cannot design for everything, so we will do just too small. And also we are facing events that could be forgotten or fully unknown in the current situation, and I will come in a moment. The example I would like to share with you is something that we did with my colleague Frank Molkentin from Côte University. He was looking at the Eiffel region. So we had a similar event that took place, of course, with something which was much less in the quantity of rain. So we had something which was between 50 and 80 liters, so 80 millimeters. So this is not really big comparing to what we had in Nice, but consequences have been extremely dramatic. You remember maybe those images that have been affected Germany, but also Luxembourg and Belgium. And we had more than 180 victims directly and 10 billion euro damages. Something which is extremely impressive. So this is some of the pictures that we found. You see the pictures in 1910 and 2021. You can recognize the house, you can recognize the railway tracks, you can recognize the tunnel. Exactly the same event took place with the same consequences. In this case, the choice was made to redesign exactly as it was. But the same event came again with similar consequences. Of course, number of victims in 2021 was much higher, just because the density of the population was much higher, and also because most of the people they were thinking they were safe. They were not believing that something really huge was coming to them because they never experienced such a type of event. My colleague Frank was digging a little bit in the archives, and he found that in 1804 they had in the region, of course, without any pictures, something which was almost 2 times bigger than 2021. So we can imagine the consequences. So one of the messages, it's also important to look to history and try to recall what have been those major events and to try to learn regarding the design of the things. The other example I would like to take is an example which is in China, in Zhengzhou, in Henan province. In July 2021, we had an extreme rainfall. You see it on the map. And in that place, we had more than 200 millimeters in 1 hour. So which was also something that had never been observed before, and which has generated major consequences. We had more than 350 victims, especially in transport, including the subway. And you know, those stations are flooding because the city has been newly developed. So it means most of the people have no attitude, no behavior. They do not know what not to do in such a situation. And this is obviously increasing the risk of the exposed population and making more victims. So this is quite important, even if you design according to the code, to try to simulate what could be extreme condition. I'm not saying that we need to prevent, to design, but at least to know what will be the condition, to provide this information to the water professional, but also to the public, knowing that you will have several centimeters or half a meter of water within the street. You know that you will not go with this street, and also that you can wait before to go and to move around. And this is something which is quite important. One of the last I would like to address to save time for exchanging a little bit with the participants is just to come back on what to do to try to assess the magnitude of those events and to produce information that could be useful for design, for operation, and also information to the public. What we have seen in the case of several events in the Mediterranean environment, but also in China, it's quite difficult to obtain field data with sufficient quality. So you have the difficulty of having stations operating properly. You have the shape, the morphology of the river changing so much that what you are getting is sometimes totally useless. And of course, one of the solutions is to try to move for deterministic modeling, because you may say, the global behavior of the catchment will remain the same. So we can catch roughly the magnitude of the things and trying to simulate, you have the hydrology, you have the hydraulics, the sediment transport, try to assess the magnitude of the processes and to understand a little bit more of their processes. I'm just sharing one of the tools that we have used and developed for the VAR catchment in Nice, which is combining different models together for having a system which is producing hydrological model, hydrogeological, and also 2D hydraulic model, performing a regular simulation every hour. We forecast 3 days based on the past observation to try to anticipate actions and right decisions. The idea was to use the system and to have a better idea on how was generated the runoff in the upstream part of the catchment, of the Vesubie catchment, based on the situation of 2020, and try to simulate the discharge in the downstream part. So this is something that was done. You have an idea of the downstream part, which is quite severe. You see, it was really impressive to see the water coming 3,500 cubic meter per second, so close to the maximum of what the riverbed can take before to have overflow. So this is something which is quite serious, and obviously, if you go for flooding in Nice, the airport, and so on, consequences can be major. So, in fact, the model is running all the time, and the idea was to integrate and to generate the runoff and to see from the rainfall, the spatial extension of the rainfall, if we can generate meaningful hydrograph. And in fact, what we obtained for those stations 1, 2, and 3, this is the hydrograph, which is combining the two tributary merging and arriving to the gray one, which is giving more than 450 cubic meter per second. In that case, it means that we had close to 80% of runoff during such a specific rainfall event. So as we had this extreme intensity, even if the catchment is partly covered with forest and on natural environment, we had 80% of runoff during the event. We had the similar analysis, so you see how we combine and we have the different tributaries coming together. The number 4 here was just to see if all tributaries were contributing, and clearly we had nothing coming from this tributary, few things, and it was quite nice to see that the model was able to see and to produce something that was meaningful. At the very end, this is what we obtained. So this is the shape of the hydrograph in red that has been generated. You have the rainfall over there, the mean rainfall for the catchment. And here you have in blue some of the values that were recorded locally. In fact, most of those values were inaccurate because the gauging station was affected by works going on under the bridge, and so they were not able to record the low value, and they were starting only when part of the embankments was collapsing. So it means for all of those reasons, the model can give you a good idea on what could be the situation. We went a little bit more further to try to see with different type of models how we can generate interesting results. So I'm just sharing this graph, which is showing comparison. So it's a benchmark with 12 models. And what is interesting is what you have in the red circle are the 2 deterministic models we have used. So the 2 deterministic models are producing very consistent models, very consistent, and they are very close to the reality. The data-driven models, of course, because they have never seen something that big, they do not have such a type of event in their training period, are completely totally lost in most of the cases. So they are producing values that are too small or too low. And in fact, you cannot have any real confidence in those things. So I'm not saying that those models are not useful. They could be extremely useful, but as long as you can produce the relevant extreme events that should be there to train properly the model afterwards to generate the proper behavior. So you may have observed information, but you can also simulate with the model something that could correspond to extreme situation and that could be used for producing things. So just to conclude in a quick way, so the NGs have to debate. Of course, the first priority is to have an efficient forecasting system regarding the hydrological extreme events. So we need observation and we need models. In some of the region of the world, this is extremely challenging. We have also to create a very efficient early warning system based on robust solutions. So you may have something which is very simple, but you should have this organization properly organized. When you get the information, when you have validation of this information, what are the measures you implement immediately to communicate with the public and to make them safe? So this is something which is important. Another point is for the engineers, for the people who are listening today, keep in mind the possibility of the never observed events. As I said, in the case of Saint-Martin-Vésubie, most of the houses had more than 120, 150 years, and they never saw a flood than it was in 2020. So when you do your design, whatever you do, keep in mind that you may face bigger. What will you do in that case? What will be the attitude? Which bridge will collapse? Which one will be maintained? Which type of infrastructures can resist? I'm strongly advocating for having this analysis done. This is not something which is extremely costly, but I think this is something that could be very useful for improving the resilience of the structures and resilience of the population. Developing crisis scenarios, trying to anticipate actions over months for recovery phase. As I said, one of the problems on the village you have seen was to bring back water supply and wastewater collection. You know, as the village is in altitude, we were and temperature starting to drop. So if you deploy emergency water supply networks, especially in pipes that are just on the ground and not underneath, so you can have problem of temperature and the water is just frozen within those pipes, so you cannot deliver the service to the population. So it means you have to anticipate those things and try to develop resilience for the population and also for the infrastructures. Promoting resilience is something which is extremely important. We can rebuild after in better conditions. We can try to quantify resilience to have regional resilience plan in EU. So this is something which is planned for 2030, and try to assess exceptional situation, as I was mentioning. The last one is regarding the key messages to bring home. Obviously, convective events are new challenges. We have strongly to improve our knowledge, to deploy the tools to know better about them. Just to give you an idea, you know, we had a problem regarding the radar analysis, the radar image analysis in the case of the Alex storm, because the maximum threshold within the image analysis was, and we had 513. So it means we were above the threshold that was defined for the analysis of the images. So we need to be more open to this type of situation, and we need to anticipate. Keep in mind that nobody can be flood safe, whatever the situation is. You cannot flood, you have protection, you have embankments, it will collapse. Be ready to that and try to see how we can assess the level of protection and simulate extreme situation. Being prepared for extreme unexpected conditions, this for sure, knowing is saving life. Knowing for acting, so it could be monitoring, forecast, simulation of extreme things. Preparedness of exposed population is obviously a key point. It can be done through many aspects. It can be with schools, with specific communication. It can be done with drills, exercises. China is implementing a very serious program for most of the flash flood sensitive municipalities with an annual drill with the population. Everyone is aware on what to do, what not to do, and so on. And obviously, and this is for the long term, trying to improve resilience of urban environment by including urban preparedness building. So this is a message also for the urban planners and for the architect. We need to design properly to be ready of the flooding and to try to minimize consequences for the inhabitants and obviously for the infrastructures. I think I was already too long, and but I was willing to share those elements with you, and I would be more than happy to answer to your questions now or even by email afterwards. Thank you very much.